Hello and welcome to this lecture. In this lecture, we're going to start looking at some properties and details and some interesting tidbits about derivatives and how they are defined. Okay. So, let me begin with another form for the definition of the derivative, right. So, we've always seen this form limit as h tending to 0 f of x naught plus h minus f of x naught by h. It turns out another very interesting and very important form for the derivative is this one. F prime of x naught is limit as x tending to x naught f of x minus f of x naught divided by x minus x naught. Okay. So, notice what has happened here. So, here x naught plus h x naught, here I have x x naught. So, here also x naught plus h is actually tending to x naught, right. As h tends to 0, x naught plus h is tending to x naught. So, instead of having this h as the step variable, we keep x itself as the variable and denominator we divide by x minus x naught. So, intuitively we see that these two definitions seem exactly the same and you can also prove it. Okay. So, the proof again uses some simple little tricks. So, we start with this expression f of x minus f of x naught by x minus x naught. So, instead of writing x, we write x naught plus x minus x naught. Okay. X naught plus x minus x naught is the same as x, right. I have not done anything here. But once I write that, I identify that this x minus x naught is like a step. Okay. So, this x minus x naught is like a step. So, you can do a change of variables, h is x minus x naught. So, x tending to x naught is the same as h tending to 0. So, that way once you take limits on both sides, it is the same thing. So, intuitively what we looked at as the same thing is also exactly the same definition. Okay. So, in this form some things are easier because there is no new variable h, no. So, you have x and x naught and this f of x shows up here as a value, as a dummy variable here. So, it seems like a slightly different form, but more intuitive also. Okay. So, that is also nice to see. So, why is this a little bit more interesting? So, maybe I can draw a picture for you to show you how to visualize this. So, we had this. So, we have a function and you have an x naught. Okay. X naught, how do you think of the limit? So, there is this x that I have here, and then I have this little triangle here, and then maybe you can also draw this guy here. This one is f of x minus f of x naught. This guy is x minus x naught, and the slope of this line is f of x minus f of x naught divided by x minus x naught, isn't it? So, it is the same as what we did with the other thing. Okay. So, this is how you visualize what's happening with this definition. Okay. So, this is a very important thing and we will use it now. We'll see I will use it now quick enough. The derivative and linear approximation of a function is very, very important. Okay. So, now linear functions we know very well, right. See, this is just straight lines, y equals mx plus c, and then you know them very, very well. But if you look at a general function f of x, it has some crazy shape. It goes up and down like this, and it may not be linear anywhere, right. But nevertheless, if you fix a particular point x naught and look at the f of x naught and look around here, we know that zoom in, zoom in, zoom in, zoom in, suddenly everything starts looking linear. So, around every x naught, there is a linear approximation. It is not the same approximation. As x naught changes, the approximation also changes, the line changes, right. The line we know, we've seen this picture before. The line keeps changing as you change x naught, but nevertheless around x naught there is a linear approximation that you can do for any function f which is differentiable at that point. Okay. So, how is that going to work? So, for that this kind of a definition for f prime of x is very interesting, right. So, you notice here what happens. F prime of x naught is limit as x tending to x naught of this guy. So, what does that mean when you say limit? As x becomes really close to x naught, this expression is going to become f prime of x naught, right. It is going to become close to that. One way to express that for us is to say that if x is very close to x naught, I can approximate the derivative as f of x minus f of x naught divided by x minus x naught. We saw that this is true, right. Even for x squared, we saw as we made the step very small, the slope of that line simply became equal to the derivative, right. It became very close to 2, right. So, that is the definition itself. So, once you say this approximation, I can also rewrite this. Okay, I am just rewriting this, that f of x is approximately f of x naught plus f prime of x naught times x minus x naught. Now, what we have on the left hand side is f of x, the general function f of x. Of course, we are looking at x around x naught. X is very close to x naught, only then this approximation makes sense. But interestingly, what you have on the right side is a linear function, right? F of x naught is a constant, f prime of x naught is some constant, x is the only variable here, right? So this f of x has been written as a linear approximation. So this form for f of x, approximating it in this fashion, is a very, very powerful idea once again. However non-linear your f of x may be, around a particular point, if it is differentiable there, f of x is going to be roughly linear. So this is a very powerful idea in all of engineering, and you can also picture this. This equation here is a straight line. At x equal to x naught, the value is f of x naught, so it passes through the x naught comma f of x naught point, and it will be sort of approximating this at this point. Okay, so this is the equation of this line that we have here. Okay, so this is a very, very, very important idea. So this approximation can be made more rigorous. You can wait for the what's called the mean value theorem and so many other things that we will see later on, and when in the applications of derivatives we'll see this Rolle's theorem, mean value theorem, where all these approximations and these ideas are made a bit more rigorous in some sense. But for now, this itself is a powerful and interesting notion, right? That any function, however shape it may be, around a differentiable point, it's a straight line for a small interval. Okay. Of course, notice here, as I change x naught, if I change x naught to this point, this line changes. Okay, this line changes in slope. It also changes in the point where it is going to cross. So it's not one line. It's just a bunch of lines that approximate any shape as long as it's differentiable. If it's not differentiable, then this will not be true. It will go jerky all over the place. Okay. So this linear approximation is very, very, very important idea around derivatives. Okay. So one more interesting little technical detail is that differentiability implies continuity. Okay. So we saw this notion of continuity, right? A continuous function is something that doesn't jump around too much, but differentiation a little bit more than that, isn't it? So it has to be continuous, but then if it is going to have like a mod x type behavior, right? So if it is going to have a sharp turn, then even though it's continuous, it may not be differentiable. But the other way around is always true. If you have f being differentiable at x naught, then that is, this limit exists, then it turns out f is continuous at x naught. We didn't see a proof of that. I'm just going to show you a very quick proof of that. Again, the proof is very, very easy. We again do the same little trick of f of x minus f of x naught. We won't change anything, but suddenly we'll get our result, right? So what is this not changing anything? I'm going to divide by x minus x naught, multiply by x minus x naught. Same thing, right? Nothing has been changed. Now if I take limit on both sides as x tends to x naught, here I have f of x minus f of x naught. Here the limit will go as limit for this guy multiplied by limit for this guy. Limit for this guy, I know it exists, right? F prime of x naught, it's finite, exists. Then this limit is 0. So these two will multiply and give you 0. So you see here that limit as extending to x naught f of x is f of x naught, and f becomes continuous at x naught. Okay. So that's the crucial idea. So differentiability, existence of this limit also means this is true. This is what I've proved. Okay, from here I've gone here. It turns out you can't go the other way. Okay, continuity does not imply differentiability. A very easy counter example is mod x at 0. At 0 mod x, we saw this function, right? It's actually continuous. There's no problem here, but it's not differentiable because the slopes on two sides are not the same. Okay, so differentiability is a stronger notion of smoothness than continuity. Okay, this is an important idea to remember. Continuity is also a notion of smoothness, but continuity allows for the sudden change of direction. It allows for corners. You can have many corners, but still the function will be continuous. But if you say, on the other hand, the function is differentiable at many places, at one point if it's differentiable, at that point it has to be really ultra smooth. It cannot have a jump. It cannot go off to infinity here, there. It cannot have a jump, and it cannot even have a sharp corner. It has to have a smoother behavior. Okay, so differentiability is one level of smoothness higher than continuity in some sense. Okay, differentiability implies continuity. The other way around is not true. Okay. Final technical detail which I've just generally skipped so far, but if you study more formal mathematics, these things will become very important. A notion of a domain of a function and how it restricts the meaning of limit and derivative. Okay, so basically so far we've always considered domain to be all reals, right? If I say f of x, it's from real to real, and x can be any real number, and this f has to process it and put out the value. Okay, but that need not be true. Okay, there are a lot of interesting functions that are defined only for some values. Like for instance, even x power a that we saw, right, root x. Root x we don't define for negative x, no, it's only for positive x, isn't it? So things like that, there are a lot of interesting functions which I was implicitly using only for some ranges, but I was not bothering with all that very carefully for a theory, from a theory point of view. So theoretically, what you have to use is domain of a function. You should say f is going to take values, it's going to process values, input for x, input for f, input for f will come only from this set which is the domain of f. Okay. So this can be a smaller set, it need not be entire real number. Okay. So our functions have so far been entire real number, but that need not be true. So many cases domain may be restricted. Like I said, positive x is very common description. There are more fancy functions like logarithms, you may have heard, they also work only for positive x. So positive x is a very common restriction, or even negative x for some that matter, or some restriction like this. You may want to restrict x to some interval or some crazy restriction. You know, I mean, you can do all sorts of restrictions there. Okay, for whatever reason, your function may have this kind of restriction. If that is true, you have to be slightly careful when you define limit and derivative. What you have to be careful about is the following. Okay, if you want to think of limit of a function at x naught, okay, and if it has to be well defined, this will happen only when some interval around x, small delta interval around x, like x naught minus delta, x naught plus delta, right, around x naught, there should be a small interval which is in the domain of the function. If no such interval is there in the domain of the function, defining limits and derivatives is not very meaningful. Okay, so that is something you have to keep in mind. However, there's one point I want to make. Supposing this function is at the corner of the domain, like for instance, if the function is defined for a and b both inclusive, and you want to think of the derivative or limit at b, only on one side it will exist, right? Limit will exist only on one side, like b minus will exist. B plus is meaningless, right? There's no domain there. Likewise, derivative also, we have not seen one-sided derivatives yet. You can define one-sided derivatives. So derivatives will only be on the left side, like the slope on the left side, right? So this notion of restricted domains for f, I have not really bothered too much about, but you know, this is an important consideration if you want to be rigorous about definition of limit and derivative. Okay, so I'll conclude here in this lecture. I think I showed you a few of the small details that you have to be careful about, and some very interesting properties, in particular the linear approximation. It's a powerful property. We'll exploit it as we go further. Thank you very much.